Hello. Hi guys, good morning. Welcome back to the video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see a problem. Find the punishment number of an integer. Now, it simply says that you are given a positive integer n. As you can see, you are given some n, and you have to return the punishment number of n. Now, punishment number of n is defined as the sum of squares of all the integers I such that I is from 1 to n, and the decimal representation of I square can be partitioned into continuous substrings such that the sum of integer values of these substrings is equal to I. What I mean by that is, okay, what you will do, you will have to iterate on all the possible values of I, he is saying from 1 to n. N is 10 in this case, which means I will go 1, 2, 3, 4, up to so on and so forth, up till 10. Now, for each specific I value, right, let's say I take the I value as 9. So for this is one such I value. So I value here is 9. For this I value, do a square, which is 9 into 9. It becomes 81. Now, with this 81, make sure that, you can convert that to a string. If you convert that 81 to a string, okay, it becomes 81. Now, can you partition this into continuous substrings? Again, this is one such substring, this is one such substring, next such substring. So it should be continuous substrings. And then he is saying the sum of integer values of these substrings partitioned into substrings such that the sum of integer values of these substrings equal to I. So sum of integer values, so okay, int 8, integer value is 8, integer value of 1 is 1. So you achieved a value of 9, which is equal to I, and that is the reason this is a good one. So I have to take the summation of squares. So if it is a good one, if this 9 is a good one, I will take a square, which is 9 square, and add it to my summation, which is my answer. And all such I will add their squares in my sum and get them and result the answer. So for in this case, 1, 9 and 10 were good. So I added 1 square, 9 square and 10 square. It became the answer of 182. And that is how I returned it. So how I will do it? Again, do exactly as what they have mentioned, which means just try to do exactly what they have mentioned. What I will do? Okay. First task was iterate on all the integers from 1 to n, which is simple iteration of all the integers. Now, as I will iterate on all the integers, I will have to find the square value. Square value will be I into I, right? Now, my main task was that can I partition this square value or not? Is the question. Is a simple question. So again, which means that imagine you are given, because obviously when I do a square of any number, it will become something like, let's say 1 8 4 2 3 2 4, like something of this sort, like that it will become something of this sort, which ultimately indicates it's kind of some digits which are coming up. So I will, let's say 1 8 4 2 3 2, let's say like this. Okay, so there are some digits which are coming up. Now you have to partition it. Okay, either you can partition like this, this, like again there are multiple ways. If I ask you how many number of ways are there to partition this, you will ask, Aryan, there are multiple ways. So for the first partition, how many ways I have? I can do like this, or this, or this, or this, or this, or this, or this. For second partition, how many number of ways I have? I can do like this, or this, or this, or this, or this, or this. So again, you will see that I will have multiple ways to do a partition of this specific input, of this specific input square. Again, I will name it as square. So I can easily say that, let's say if you do a partition something of this sort, right? Then what can I easily say? That you did partition here, you did not do partition here, you did not do partition here, you did partition here, you did not, yeah, you did partition here, you did not do partition here, you did partition here. So isn't it that if this square size is, let's say, SS, which means square, and this is size. If the square size is SS, which means if this length of the string, technically it's a length of string. If this is, let's say, L, then obviously at every index I have two options. Either I will partition there or not. I will partition there or not. So it will be 2 raised to power L number of substrings which I can form. Okay, not substrings, but 2 raised to power L number of possible options of these patterns which I can form. Which means, okay, one such pattern is that I will divide like this. Other such pattern could be I divide like this. Other such pattern could be I divide like this. So these number of patterns can be 2 raised to power. Now again, before we go ahead, please make sure the like target of this video is 100 likes. So if we can do it, that will be pretty helpful. Now coming on back, so we realize, okay, these are the number of options. Now firstly, before we are going ahead, let's make sure that whatever we are trying to do here should be achievable, which means that I was trying for all possible values from 1 to n. So it will iterate O of n time already taken here. Then it will find the square. Okay, this is the O of 1 operation. And then I will call some function which has to technically try for all the possibilities of substrings which can be there, which is 2 raised to power L. It entirely depends upon the length of the string. What is the length of the string? So it can go pretty high. Make sure that we are good with understanding the n value and how much it can go. Okay, it says that n is 1000, which means, okay, this is, let's say, O of 1000. Now if I do square of any number, obviously, let's say if I take the maximum number 1000, so 1000 is 10 to the power 3. If I do a square, which is nothing but 10 to the power 6, how many digits it will have? Obviously at max 7 digits. How I can say that? It is nothing but number of digits, in this value of 10 to the power 6 will be log base 10 the value of n square, right? This is the number of digits. Again, this will give you 6, but technically 6 and 7 are same, roughly same. So you don't have to worry about it. So this will be 2 log n to the power like to the base 10. This is the number of digits which I can have in a number n square. And again, this I have taken maximum number of digits. So if these are the number of digits, I can simply replace again, because these are the number of digits I can have. Obviously, this is the length also. So I can easily say this L will be nothing but 2 log n to the base 10. If I just simply replace it, it will be 4 log n to the base 10. This will be, this indicates I have to try for all these possibilities. I have to try for all these possibilities. Okay, let's proceed forward. Again, you will see that people are simply removing this 2 also. It also works. Again, that's not a very big deal. Cool. Now my main task is, okay, let's try for all the possibilities, which means that I had a 1, 8, 4, 2, 3, 4, 2. Then again, I will simply call this can partition. Can I partition this or not into continuous substrings such that the sum of them, which means I have to take here 1 plus 842 plus 3 plus 42. This should technically be equal to my I. This is my target now to achieve. If this partition can give it, and again, for me, the only question is any such partition. I don't want to know the actual partition itself. Any such. So basically this string, which is the square of I square, which is the I square, it should at any partition give me this relation and I will be good to go. So now, which means I can easily say that my can partition, which is a function, I can simply pass it a string. Obviously, I told you that at every index I have option, which means at this index I have option that will I do a partition here or not. So obviously I will start off from the index 0. Ultimately, I also know that whatever I am doing, I will have to convert that substring portion into an integer and make sure that I'm keep on adding that. And because I want to achieve the target summation of I. So I also know the target sum. That target sum, again, this target sum is nothing but I itself. Okay, this is my starting index. So you can say this is the starting index. Now let's start with the fun part. It's now a simple recursion. Again, if you don't know what recursion is, make sure that you go and check out, practice problem sheet. In that, you can easily practice easy to medium questions of recursion, and at least you should be good with that. Coming on back, Now I can simply say that in a simple recursion, the simple base case is that if my I, which is the index, if it reaches the end, let's say end here is, I'm saying s dot length, sorry, for C++ it is size. So if it is s dot size, I can simply say that, okay, I have reached the very end, and now I can simply have a check that, whatever is there, like condition should satisfy. Again, base conditions usually you can write independently, but it is good that firstly you write the main recursive condition and then you come back to the base condition. Now let's come on that what will be the main recursive condition here. Again, if we will need it, we will memorize it. If not, then we will skip it. Let's see. Cool. So firstly here we realized that, I will have to find the sum. So okay, I took the sum. Then I also realized that I will have multiple possible options, possible options to do a split. I can do a split here, 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 and so on and so forth. So I will simply say, okay, bro, I am at this specific index, right now. I have options to split. Either I can split here, which means, at this index, or maybe next index, or maybe next, and so on and so forth. So I can try for all possible indexes for split, starting from my current index. And then I will simply keep on going s dot size and then I plus plus. Here I will simply say, okay, now this indicates I have option to split. I can split here. Again, either if I split at the index I, which means I am splitting here, or at next index, maybe here. So if I am, let's say, splitting here, so I have to firstly maintain the sum. Now there are two ways. Either you can take a substring from index to I. You can take a substring from this index. Index is the your current index, and I is what you are trying. Up till what point you are actually taking a split. You can take that substring. In this case, it will be 1. Just convert that to an integer, which is 1 again, right? Because again, this is a string now because you're treating on a string. And then after converting that to an integer, which is 1, you can simply check for the remaining portion. So how I can do? I can simply check for remaining portion and say that can I partition starting from the next index, which is obviously I plus 1, right? Again, I'm not copying s, so s will be as is. Starting from the next index is I plus 1. But now my target was, my maqsad, my aim was to achieve a target summation, which means that entirely like this plus this plus this plus this should be equal to my target I. So either you can keep on maintaining the sum, that's one way, or you can say that, okay, what is the remaining target? What is, because obviously if 1 is included, now the remaining people have to sum up to I minus 1. I minus 1. So I will say again, here I make sure this was target sum, this was target sum. So now I will simply say that I have to achieve a target sum minus the current number, whatever I had, or I should say the current sum, whatever I had. So I will simply say current sum. Again, you will see why I'm taking current sum, but imagine this is the substring value. Cool. So this, whatever is the sum so far, here it is 1, let's say. I will just simply say that target sum minus sum should be achievable starting from this index. If it is achievable, then make sure that it's a happy case, return true. If not, then try for other possibilities of splitting at the corresponding index. Now, why I say splitting, which means, let's say if it is not possible, which means you did the first split here and then your recursion tried for this portion of doing the split. Next time you will try for 18. Now you had already tried for, you had already done the computation for 1, which means that you had taken that specific string, converted to an integer. Now you only received a 8. Why can't you just simply multiply this 1 by 10 and add a 8? You will receive a 18, right? What if next time you have to take 184? Simply multiply this by 10, add a 4, you get a 184. So rather than taking substring again and again and converting that to an integer, which is again in worst case O of 2 log n to the base 10, which is a 7 operation. Again, it is a 7 operation. Again, let's keep it like this only because it is roughly this, 7. So I can simply say that this will be 2 raised to the power 7 or 2 raised to the power 6, which I can easily go about. Cool. Which is this, 64. Now coming on back, I realized that okay, it's pretty okay for me that where it is gone. Yeah. So, yeah. Cool. Now, yeah, it is simply mentioned that if I would have taken the specific string and then converted that, obviously I would have incurred this O of 7 complexity. But then I can use simple math. Simple math says that, bro, you had already computed one, or let's say you have already computed 18. Just simply have to take this one, right? Because you have to try for all the possibilities. Try for all the possibilities. All the possibility says that I will try for 1, I will try for 18, I will try for 184, I will try for 1842 as the first digit or as a first string. And again, if let's say I tried for 1842, the next I could try is for 2 or maybe 23 or maybe 234 or maybe 2. Let's see if I try for only 2. Okay, next I can try for 3, 3, 4, 3, 4, 2. Okay, let's say I try for 3, 4. The next is okay 2. So this is, let's say, one such pattern I can form. Now, I will simply mention that the entire essence was that I can take 1 and maybe 18 and 184. Just to compute that next thing, I can simply take my summation, existing summation into 10 plus the current digit, which is s of I, because it's a character, convert that to a digit, which is minus 0. So this is how I can achieve the actual summation, which is this specific thing I can achieve as a digit very easily in O of 1 time rather than O of a 7 time. Cool. Again, if I would have used string, I would have achieved that in O of 7 time, but now I'm using it O of 1 time. And ultimately, there's one pruning check which you can apply. The pruning check says that how to stop your recursion as early as possible. That pruning check will simply say if the sum becomes more than your target, obviously if the sum itself, this sum itself becomes more than your target, obviously target minus sum will become negative, which is obviously never possible because you have to achieve exactly equal to target, right? Now I will simply say that if that's, sorry, this is not the target, yeah, this is the ultimate stuff. So I'll simply say if the sum is more than target, simply return false, return false. Okay, if I return false, then what else? Okay, if I try for all the possibilities, it never became true, then also return false. Also return false. Now I can easily apply my base case. My base case will simply say that, okay, if I have reached the end, I made sure at every point in time my target sum was being reduced with the corresponding sum of digits which I had of the substring which I had. So if it is reached here, which means my target sum should have become 0 at this point. If it is 0, it's a happy case, return true. If not, then return false. And that's your simple recursion which you can apply. Make sure that this scan partition will be a boolean because it returns true or false. And that's how you can simply solve it with the help of recursion. Obviously, because you are going on, I told you that what is the complexity for this. Complexity for this entire recursion to try for all the possibilities will be 2 raised to power, log n, you can say, or maybe you can say it is 4 raised to power log n to the base 10, which is for the complexity for trying for all the possibilities, and inside it I'm just applying it O of 1 operation. And the main portion is this when you're trying for all the possibilities of indexes. Ultimately, if I club this up, it will be O of n into this thing, which is O of n into 4 log n to the base 10, right? Again, it is O of n into log n to the base 10. This is your time complexity for this entire approach. And obviously, what will be space complexity? Space is nothing but recursive tree, because obviously you're not using anything. It is entirely a recursive tree which you are maintaining here. So the space will be that its corresponding recursive tree. Recursive tree will simply say, okay, I have some set of digits, let's say again, let's take same 1842, 1842, 342. So either I can take, let's say 1, let's say if I take, let's say 18, then it is one such possibility. Okay, 18. Then I had 42342. Then I could take 4, let's say, or let's say, yeah, I take 4. Then next possibility is 2342. So again, other possibility could have been let's say if I take 184, and then the other possibility could have been 342. So you see that this entire recursive tree depth could actually go in worst case up till, let's say if I take again, so if I take, it will be 342. Let's say if I take, it will be 2. So this is the entire recursive tree depth right now. But in worst case, how much it can go? It can go up till, let's say if I make something like this, like 1, and then next is 8, next is 4, next is 2, next is 3, next is 4, next is 2. So it can go up till, the depth can go actually up till the number of digits. And I told you number of digits is nothing but 4 log n to the base 10. This is the number of digits which I have. Not really. Number of digits are log n to the base 10. 2 log n to the base 10. So this is the number of digits. So technically this will be corresponding space complexity. Now, cool, let's see the code. It's exactly same as what we discussed. And again, this will work because my n is 1000. So 1000 into 4 into log n to the base 10, which is, if I take 1000 here, it will be 3. And this will simply work for us. And again, space will also work. Let's see the code. It's exactly same as what I showed you, that I will take a total summation, which is my final answer. I will go on to all the possible I values. I will take the square. I will convert that square to a string because I have to run my recursion on top of it. I will say it, can I partition it? And I will pass in the square string. I will pass in the starting index, and this is my target sum. My target sum is what I wanted. Then I will simply say that, okay, now you have this corresponding sum. This will help me to apply O of 1 operation to find the corresponding digits, or the actual digit value. So I will compute a digit value here. Then I will have a pruning check that, if the sum is more than target, then simply break or return false. No, yeah, sorry, not return false, but break. Because why I'm saying return false? Because obviously you can return false from here also. So here, let's say if I can partition, here, then obviously I will try and reduce the corresponding target sum. If it is possible, if it is possible, this thing is possible in future, return true, because this thing will return true ultimately if you give him the target as 0. Again, this is the basic recursion. If you don't know, you can just go and check out this thing. If not, then this is a specific answer. Now, the only use case here is that would you like to try for a memoization here? Firstly, memoization helps you to improve the corresponding type complexity. If, let's say, you memorize things, what time will you improve? Is the question. If you memorize things, what time will you improve? Now, you might say that, Aryan, 1842, 342. So what I can do, Aryan, I can memorize this portion and this portion. That, okay, for this portion, what is the corresponding target sum and is it achievable or not? That is one thing. Okay, like I can just pre-compute this. Okay, it is able to achieve this specific target sum, and then I will try to find the target sum for remaining stuff. Maybe you can try it, but you will see that now what is happening, you, rather than being dependent upon index, now you're dependent upon target sum as well. No worries, even if you are trying it, you will have to incur the specific space for it, which will increase the space nearly equal to corresponding time which we have, and ultimately no improvisation in time as such. Sorry, yeah, in time as such, but worsen the space, and that is the reason there is no point of even applying DP here. Cool. Again, because again, you saw that even if I apply it as I showed here in this example, I will, let's say, memorize that for this piece of portion, that what specific target sum can be achieved for this all thing, and then I will try for the remaining portion, can I achieve the remaining sum from my target which I have. This is the same way saying that I have to keep on track for a specific index what is the corresponding target sum achievable, which is ultimately saying that you have to maintain target sum, all the possible sums up till every index, and that's unnecessary because this will actually improve worsen your space but not optimize your time, because time will still remain same. Cool. I hope you guys got it. Bye bye. Take care. And make sure that you check out the participants. And again, like, target, unlikes, please do it. Bye bye.